welcome all the students and teachers for this second memorial lecture for Dr. Mrs. Mangala Narlikar, and this lecture is given by Professor V.M. Sholapurkar. Professor Sholapurkar is a former professor and head of the Department of Mathematics, SP College, Pune, and he is currently the trustee of the Bhaskaracharya Pratishthan and also adjunct professor. He will give the talk on an elementary proof of Abel's theorem on quintic polynomials. Over to Professor Sholapurkar.
So, let me first pay my highest tribute to Dr. Mrs. Mangala Narlikar. We worked as colleagues at two places. One is Bhaskaracharya Pratishthan, where we both worked in the capacity of governing body member. And second place is Bal Bharati, where we were on a committee for writing Bal Bharati textbooks for school students. And at both the places, I learned a lot from her. Especially at Bal Bharati, it was an excellent job, an outstanding job, and I learned so many things that how to write for small children. Especially, she was very enthusiastic and very innovative in the sense that she could write poems, stories, which were readily accessible to school students, kids. For first standard, second standard, it is very difficult to write textbook, and she was our leader in that project, and I learned many things from her. So I am thankful to Bhaskaracharya Pratishthan for providing me chance to talk in this memorial lecture series. So now let me come to this topic. So first of all, let me tell you that this elementary proof of Abel's theorem is not my proof. I am just presenting this for the students of mostly undergraduate, postgraduate students who are present here. So mainly lecture is meant for students, and the word elementary is subjective. I mean, I think that it is elementary. Then generally, the theorem is dealt with in postgraduate syllabus, and generally Galois theory is applied for proving that the quintic polynomial cannot be solved, or the solutions cannot be written in terms of radicals. So generally, it is taught at the second year postgraduate courses towards the end of field theory course. That is the general experience. But this proof that I would like to present could be accessible to undergraduates without knowing Galois theory. Okay. So without knowing any field extensions, group theory, anything like that. Though implicitly there could be, one can find out some correspondence between this proof and Galois theory, and so ideas might overlap, but the terms and concepts that I'm going to use be accessible to any undergraduate students. So two things are required to understand this proof. One is elementary complex numbers. Now that is also very, kind of tricky to say. Complex numbers and complex square root function. Okay. Now understanding that is elementary or not, I don't know. It is left to you. I will come to that. That is one thing that is required. Other thing is permutations. Okay, which are apparent in the Galois theory proof also. So these two are main ingredients in this particular elementary proof. This proof is given by Arnold, a very famous mathematician, Russian mathematician. He gave this proof around 1963. But no written version of this proof, his original, whatever he presented, was not documented in some sense. And there he delivered lectures for undergraduate students in Russia at that time, and one of the pupils in that audience took down notes and later on wrote a book, and then it was further simplified and so on, and people still have interest in this particular theorem, which is in a way kind of very fundamental, pioneering result in algebra. If it is all about solving polynomial equations, this stands very differently. It has a different glamour also, and people are still interested because there is a paper in 2022 which further simplifies Arnold's original lecture series, where he used a lot of topology, okay, some concepts which may go beyond undergraduate curriculum. So till 2022, mathematicians kept simplifying that, and this final version, perhaps I would like to present in front of you. So let me start. So this is background of what this is. Okay, so I started 5 minutes late, so I will take, because this is a very long story which I want to cut short, but still let's see how one can manage. Okay, so therefore I will not give much historical comments, because solving polynomial equations, a lot of history is associated with it, and if one wants to talk about it, it will take a semester long, giving all historical details and all that. But let us begin at the beginning. That is, we are talking about writing roots of a polynomial equation in terms of coefficients. That is the theme in particular. So simplest equation to start with is linear equation, say, and I am considering only one variable. Yes, so let's start with ax plus b equal to 0. Linear equation in one variable, and all coefficients I assume to be complex numbers. Okay, so a, b are complex numbers. Okay. And I allow solution also to be in complex number set, so that we know that whatever is degree, suppose degree n, then there are n solutions available in the set of complex numbers. So there is no problem. So generally, I will take this a to be 1, leading coefficient to be 1, which one can do, but let me keep it like this here, and then I can write x equal to minus b by a. Okay. Where a and b are coefficients, so this is a rational function of coefficients. Okay. So for linear equation, we don't have problem in the sense that how root is, there is only one root, and that root is minus b by a, and this is a rational function of the coefficient. Coefficients are not rational, coefficients are complex numbers, but the function that it represents is a rational function. You understand this? Okay. All right. Now let us go to quadratic. I will take leading coefficient 1. Okay. Just to make a comment, this is also known from Babylonian days and so on. As I told, I will not get into history, but there is a long history associated with solution of quadratic equation. Even in the Indian setup, Brahmagupta gave complete solutions of the quadratic equation case. And we all know how to solve this. Okay, we know how to write solution. So minus b plus minus root b square minus 4c upon 2. Okay, that is how to write the solutions. Now, what do you see? What is difference between these solutions? So there are two roots. Okay, both roots are expressed in terms of coefficients. But do you see any change in the type of function that is used? Yes? Now, this is no more, only a rational type of function. There is some square root sign. There is a radical appearing in this formula. Okay. Now, I will go ahead and write cubic also. Okay. See, if you go back in the history, down say several hundred years, one doesn't know. You give an equation, you try to write the solution, and what you know is only coefficients. So you try to write roots in terms of coefficients. Okay. So after say success of quadratic equation, then one wants to solve similarly cubic equation, and wants to write equation, so roots in terms of coefficients, cubic. So suppose you have x cube plus say bx square plus cx plus d. Okay. See, there is a standard transformation which eliminates the second highest degree, okay, which is in some sense here also you can use this. Okay. See, in this case, the sum of the roots is minus b. So average root is minus b by 2. So if you put x equal to y minus b by 2, okay, then this second degree term vanishes. Same trick would work here also. Here the average root will be minus b by 3. So you put x to be equal to y minus b by 3, and then this square term will vanish, and then you will get x cube. Okay, you can write y cube plus say py plus q equal to 0. Okay. So this is linear change of variable, which brings this equation into this form. And one cannot easily write the roots, so I have written this. I will write down the roots for you. Okay. Anybody by chance knows how to write roots of the cubic? Because such thing was there in curriculum many years back, especially 30 years back. But now the solution of cubic and biquadratic is no longer in the standard curriculum, so no chance. And even if it is in curriculum, it is difficult to just write it like this. So suppose this y is written as, so you look at this, cube root of something minus q by 2 plus root p cube plus by 27 plus q square by 4, okay, plus something which I am not interested in. What I want to show is, yes, now do you see any difference in the way this solution is written, quadratic and the cubic one? The form of the solution in terms of coefficients. Yes, here. And you look at this. This is the kind of trivial case. So what do you see here? There are two radicals. There are two radicals here. Okay. You see this? This is a radical sign here, and there is one more radical inside that. Okay. Now you guess that suppose if I go ahead and write quartic equation, that is degree 4, okay, say x4 plus bx cube plus cx square plus dx plus e. What is it? So degree 4 equation. What do you expect? 3 radicals. Very good, because there is one radical here. There are 2 radicals. There could be one more radical here. And I will not now write down, because one can write down, they are very complicated. Okay. There is something called resolvent cubic of this. Okay. So you reduce this to cubic case. This is done by the way, by Cardano, Italian mathematician, in 16th century. Okay. So there was long gap between quadratic and cubic writing solutions. Okay. See, even Brahmagupta, if you take a Brahmagupta is 7th century. This is 16th century. Okay. Cubic was completely, the solution of the cubic was written. Okay. But at the same time, biquadratic, that is quartic equation solutions were also found. In fact, in the same book, you find both the cases. Okay. The other one is given by Ferrari, who was working with Cardano at that time. Okay. So there are roots here. So I will just tell you idea. There is some associated cubic, which is called resolvent cubic. Its roots will look like this, and square root of those roots will appear in the formula. So there will be one more radical. Okay. So now one wants to continue this. Okay. So you want to write degree 5. Okay. And then expect that degree 5 also one should be able to write in terms of coefficient. At worst, what can happen? You will have one more radical. Okay. Okay. I would have asked you a question, what will happen? You will say, now there will be one more radical, because that is the pattern that has evolved up to degree 4. Okay. But that's the miracle or nice, I don't know, nice or bad, but nice thing that has happened, that you, that the Abel's theorem, which says that you cannot write now. Now this process doesn't get continued in some sense. Okay. But that we know now, if you solve biquadratic, you will try for quintic. So people tried. In fact, I will tell you one formula which is written by Euler, okay, in the 18th century. Okay. And Euler conjectured that these roots are of the form. So now I am considering quintic polynomial. And the roots are fifth root of some a1. I will tell you what are a1, a2 plus fifth root of A3 plus fifth root of A4, where again there is some resolved one biquadratic associated with degree 5, and Euler conjectured that the roots of the original will be of this form. So, one more radical, because these are roots of biquadratic and so on. Okay. But he could never prove that, of course, because we know now that it was impossible. Okay. But even someone like Euler thought that yes, one can now go ahead and write the solution of Quintic also in terms of radicals. Okay. And then not only Euler, many great mathematicians kept trying. Abel, so as I told you, I will not tell the entire history in between Euler, what happened, what Gauss said, what was take of Newton on this and all that. But ultimately Abel proved that it is not possible to write the roots of Quintic equation in terms of coefficients as function which uses only algebraic operations and radicals. Radicals means extracting roots, that is square root, cube root, nth root and so on, and any number of radicals, that is you take, okay, this is nested radical. So, any number of radicals you may try to use, you cannot write roots of Quintic in terms of the coefficients. That is Abel's theorem. So, that is some kind of impossibility theorem. Okay. See, remember, you know the relation between coefficients and roots, so called weightage formulae. Weightage formulae, that means if the roots are R1 and R2, here R1 plus R2 is minus B. All of you know this? Sum of the roots, this, and product of the roots, see, same formula will work here. Sum of the roots is minus B, sum of the roots taken 2 at a time is C, product is minus D, like that. Okay. That means what? Coefficients, okay. So, this essence of weightage theorem is coefficients are rational functions of roots. I want to add a word here. Can somebody suggest? Look at this, R1 plus R2, R1, R2. Yeah. So, symmetric functions of the roots, okay, symmetric rational functions of the root. Okay, this is very important, whereas roots are not rational functions of coefficients. Okay. So, there is some kind of tension in the relationship between coefficients and roots. Okay, one can say, okay, you can think of two entities and their relationship, there is some kind of tension. So, roots, it is not rational function of, but coefficients are rational functions of the roots. So, coefficients are nice with roots, but roots are not. Okay. This tension has come up on the surface when Quintic polynomial comes into picture. Okay. So, now let us turn around the table and say that, okay, this is formula for quadratic. Can we have a formula which is in terms of only rational functions of the coefficients? And this is one formula, but can there be any other formula which is only a rational functions of the coefficients? Can cubic formula you can have by using suppose only one radical or without radical? Okay. So, these are also impossibility theorems in which the Quintic fits. So, here I will say that quadratic cannot be, now I am saying a kind of impossibility result, the roots of quadratic cannot be written by only using operations of addition, multiplication, division and subtraction, that is only the field operations on the coefficients, and the rational functions of that is not sufficient to express the roots of quadratic. Okay. So, this is the impossibility theorem again, not just quadratic, for any polynomial degree n bigger equal to, because then you can have two roots and do the same thing. Cubic, I can say, an impossibility theorem, I can say that solutions of a cubic cannot be written in terms of the operations on the coefficients and one radical rational function and one radical, then cubic solutions cannot be expressed. I am saying cannot be expressed. Okay. In this theme, the quintic will fit. Okay. But quintic, you will say that only now biquadratic you cannot express unless you use one more radical. Quintic, you want to say that at least the language fits, that any number of radicals you may try, you cannot express the roots in terms of coefficients. Is this clear? Okay. So, now let us look at the impossibility first result of quadratic and cubic, then you will be able to guess that how quintic result comes into picture. So, let us write this quadratic. Now, for that, as I told you, it has some bit of complex numbers. So, all of you know what complex number. Okay. I want to use square root function. So, I want to use something like root z. Okay. Which is, have you thought about this? What is the square root of z function? Yes? Huh?
If we take Euler's form and represent it as e to the power I theta, r e to the power I theta, then I can turn it into some exponential problems.
Yes. So, suppose if I write z as r e power I theta, then I can write z power half. So, this I can write r times cos theta plus I sin theta, and I can express this as r to the power half cos of, yes, theta plus 2k pi by 2 I sin theta plus 2k pi by 2, and k takes value 0, 1. These are two roots of, this is called de Moivre's formula, and which you can take to nth root also. You can write nth root of a complex number, just write 1 over n, 1 over 2k pi by n, like that. Okay. So, nth roots also you can find like this of a complex number. Now, first of all, my question is it a function? If it is a function, is it a continuous function? Z going to z to the power 1 over n, okay? Or you may think z to the power half, suppose, to start with, okay? Now, see, like real variable, two real variables x and y is equal to fx, you cannot have, you do not have facility of drawing in one graph. So, you consider this as z plane, and this is w plane, where w is z to the power half, and try to think what happens, okay, as values of z. So, there are two roots for every z, right? So, if you consider, so this theta is argument of z, and as you know, if theta is argument, theta plus 2 pi is also argument, theta minus 2 pi is also argument. So, argument itself is a multi-valued quantity, okay. So, even if I fix some range, okay. So, suppose if I fix range, say minus pi to pi, okay. Then this line is not kept, so I will make it less than or equal to pi. Now, it is defined, suppose, on the entire complex plane, okay. So, how do you see this then? So, this is, now again there are two square roots. So, still it is not single valued, okay, still it is not single valued. Even if you consider z fix theta, okay, you will get two values of z to the power half. Is this clear? Yes. So, one value will be on this side, because this pi by 2 minus pi. So, theta here will be, the argument of square root will be theta by 2 and theta by 2 plus pi, okay, because k equal to 1 is 2 pi upon 2, okay. So, theta by 2 is k equal to 0 case, and k equal to 1 you will get theta by 2 plus pi. But if theta is in this range, theta by 2 is in minus pi by 2 to pi by 2, and then theta by 2, so this is another function, where if you take the other square root, it will go this side. So apparently there are two functions, f1 and f2. Okay, which now are single valued. Okay, but the codomain is only this half plane, and it is this half plane. Okay, so I don't want to get into the details further of this, but what I want to say is, important thing that you should notice, that suppose if I take e raised to 2 pi I t, this complex number particular, and I want to take suppose square root. Okay, then what is square root of this? I mean, e raised to pi I t or minus e raised to pi I t. Okay. So suppose if I choose one particular case, and now hope that it will be well behaved for t equal to 0. So this is a circle. Okay. T equal to 0, you will get value 1 of this square root. So square root of 1 you will get 1. Okay. But this point is also represented by t equal to 1. I put t equal to 1, then I get minus 1. So square root is shifted to the other square root. Okay, there are two square roots, 1 and minus 1, and I have chosen a specific branch actually, e raised to 2 pi I t. But when I go one counterclockwise loop around 0, then what I observe is that the root is shifted from 1 to minus 1. Okay. So if a loop is there, then a loop around origin shifts the roots. That is what we have observed here. Okay. So 1 at this point, but same point even if I go around, because simple reason, because the argument becomes theta plus 2 pi. Original argument was theta, k equal to 0. Now argument is theta plus 2 pi. So theta by 2 plus pi. Okay, so original theta is 0, then you will get minus 1, the other root. Okay, so this is the crux of the argument of the Arnold's proof of Abel's theorem, that if you take a complex number, okay, and take its square root, and then if you take a loop, okay, around origin here, because there are reasons, because z equal to 0 is branch point in some sense, because at that point there is only one root, okay, z equal to 0. Then the root shifts from one root to the other root. Okay. Now it will take a long time to convince you, but this you can believe from this, that if you take cube root instead of square root, and if you take one loop round, then the roots will shift from one root to the other. Okay. Okay, because theta plus 2 pi by 3, whatever. If I take n equal to 3, okay, n equal to 3 here, k equal to 0, 1, 2. So roots will get shifted, okay, from one root to the other. All right. Is this clear? Okay. All right. Now let us go to the quadratic case, okay, and suppose R1, R2 are roots. So let R1, R2 be roots of quadratic, the roots of given quadratic. What I am proving now? I am proving that you cannot write the solution, or you cannot write these roots as rational functions of coefficients without using radicals. You cannot write that. That is what I am proving now by using this discussion. Okay. All right. How do I do that? So consider a permutation 1, 2 on two symbols. Okay. Now this is not just, so this is not just a permutation. Its action on the roots has to be understood properly, because when I write 1 to inverse, okay, this means R1 goes to R2, R2 goes to R1, but the action also includes orientation, in the sense that if I write 1 to inverse, then the loop is traversed in the clockwise direction. So, one is anti-clockwise, other is clockwise. Though 1 to inverse is 1 2, okay, as a transposition, its inverse is itself. But then the orientation changes when I traverse the loop in the different direction. So, that is how, so this acts on roots R1, R2, acts on R1, R2 in this particular way, as I told you. That is R1 goes to R2, R2 goes to R1, and I am shifting the roots. I can do it like this or like this. It could be clockwise or anti-clockwise. Accordingly as, okay, this shift of, this will shift it. If there is a loop, then we shift it. Now suppose the roots are written in terms of coefficients as rational functions, then what contradiction do we get? So even if the quadratic case is clear, then the rest can be understood easily. So suppose I write R as function of my original quadratic is suppose x square plus bx plus c equal to 0, and I write this as function of b and c, where f is only rational function by using only algebraic operations. Okay. And similarly R2, suppose f2 is also a function of bc, where f type function, I will write f type means only field operations, plus, minus, product and division, okay, and rational function. F type means only rational functions by using this. So you use coefficients, then you can perform addition, subtraction, whatever, and consider rational functions of those operations. Then whatever you get, so suppose roots of quadratic can be written. Now we want contradiction because we already know that it cannot be done. So this is kind of impossibility result we want to show. Yes, can you guess? See, when I act this permutation 1 2 on the roots, R1 is shifted to R2 and R2 is shifted to R1. Then I expect that F1 also shifts to F2 and F2 to F1, unless you have equal roots. But I am talking about general polynomial, where roots may not be equal, okay? Especially when you may consider polynomials where roots are not equal. You can think on this argument only on such polynomials, for example. But if this permutation takes place, okay, R1 goes to R2, then the coefficients being symmetric functions of the roots, coefficients will remain as they are, because even if R1 goes to R2 and R2 goes to R1, coefficients are what? Symmetric functions of the roots. So B, C will remain as they are. Then F1, B, C being function of this type will not change, okay. So as this R1 goes to R2, F1 and F2 remain as loop only. So there is a shift in roots, but there is no shift here. So that is a contradiction unless the roots are equal, okay. So action of 1 2 on R1 R2 does not change B, C and hence F1, F2, because F1, F2 are of this type, okay. See, when radical will come, we have seen that roots it gets shifted. So F1, F2 form a loop, that is F1, F2 also forms a loop. This means if F1 is a complex number, then it will come to its original. So you think of suppose this plane and say suppose one root is R1, roots are complex number. And if I go anti-clockwise like this, I shift the roots and R1 goes here and R2 comes here. And this is suppose coefficient space where I have coefficients B and C. B will remain at B, C will remain at C, and F1B, F2B will also remain C. So it will form a loop like this in this space, okay. So that is a contradiction, okay. This is a contradiction. Is this argument clear to you? Now I want to go one more step further.
I'm not very much clear
Argument I will repeat again.
F1, F1, B and C remain the same. But the composition of the rational function may change. Because F2 and F1 are different.
No, like roots and all that change. If you just perform algebraic operations on B and C, the resulting number is not going to change. It is uniquely determined by B and C.
No. What I am saying is, if F1, for example, if F1 is 3B plus 4C, for example, and F2 is minus 2B plus 9C. So these things are different, being the rational coefficient or whatever in that function. That cannot say that though the B and C remain the same, F1 will remain the same.
But if B and C are same, 9B plus 3C, whatever will remain same.
No, but you are going to act.
No. Action is on the roots. Action is on the roots. So roots will change. See, if you have coefficients and roots,
Yeah.
it's a formula in terms of B and C.
But then there is what is the action?
Action on roots. See, you can always consider coefficients and roots and plot suppose both the points. So suppose these are roots, okay. Now I can transform this, so that is action by taking R1 to R2 and R2 to R1. Now I will see dynamically the coefficients changing.
Okay.
But the coefficient should remain same because the roots are same, na? So you should get same polynomial. Okay? Okay. So now next level and next level and next level up to degree 5. So I have say I will take some 10-15 minutes. I want to do that. Now I want to similarly argue for cubic, but then this action will be different in the sense that I will have to take care of radicals now. Now this square root discussion that I told will come into picture in the sense that now my impossibility result is that solution of a cubic, okay, cannot be written unless you use two radicals, okay. So this I want to prove now. So let me consider cubic case where I have x cube plus bx square plus cx plus d, and now I consider g type of functions. F types are what? On coefficients you use field operations and rational functions, whereas g type now I include one radical, okay. G type is f type and root f, okay. So I take coefficients, okay, I can perform field operation like you said 9b plus 3c minus d upon something, and also I take now square root, Now I want to say that R1, suppose there are 3 roots, is in terms of BCD, R2 is suppose G2 of BCD, and R3 is G3 of BCD. So I am trying to write the roots by using only one radical. And I should get a contradiction now. But now you have square root, and square root like f function will not only make a loop, okay, it can shift, it can trace a path from one root to the other. So I have to now use, so this is the kind of trick that is used, and that you can relate to original proof of, not original, see Galois theory proof is not original is Abel's proof, okay. And when Abel published proof, Galois did not submit his whatever writings on Galois theory and all that. So Abel never used Galois theory, okay, no chance, okay, it was done before Galois. Okay. But this is also not something that Abel did. Abel's original proof is different. But now I want contradiction, that these roots cannot be written in G type of functions. That's what I want to show. So what I do is, I can consider some another permutation. So I will do like this. So I will take 1, 2, comma 2, 3. So I will take transposition 1, 2 and 2, 3. And take something called commutator. So commutator of A B is A, B, A inverse, B inverse. So it's element like this. Okay. The subgroup of G generated by such type of elements is a normal subgroup, as you must be knowing that it is called commutator subgroup of the original group G. But let's first focus. So this means 1, 2, 2, 3, 1, 2 inverse, which is again 1, 2, right? 1, 2, and 2, 3 inverse is 2, 3. Now to save time, I will just write the answer. It is 1, 2, 3. But you can find out the answer. The product you can find out. So this is 1, 2, 3. So this is permutation on the roots. So root space. So roots will get shifted. So R1 will go to R2, R2 will go to R3. But I will show that G1, G2, G3 will remain same. Okay. That will again build a contradiction. Is this clear? So how to show that now? That is because of commutator. Because this 1, 2 will take f functions as a loop only, because f consists of only algebraic operations and rational. When we take root f function will shift to the other, like 1 goes to -1 I showed. But now 1, 2 in the opposite direction. So it will bring back the action of 1, 2, and this will bring back the action of 2, 3, whereas modulus was same anyway. Okay. So this will keep this action will keep G functions. So G1 will remain at G1. So again it will form a loop. So there will loop at G1, G2, G3 also. Here we did not need commutators, but because there is one root now, we need commutator here. Is the idea clear to you? This is main idea. So long as you can use commutator, you can resolve the problem. So under the action of 1, 2, 3 in this way, G1, G2, G3 forms a loop. So, but then this side is already shifted. Okay. So this is again a contradiction. Okay. A contradiction. Okay. So what we proved is that a cubic equation roots cannot be written as G-type functions of ABC, BCD. Is this clear? That is, you cannot write by using one radical. Okay. See, the one difference in this proof and the Galois theory proof is, Galois theory tells you precisely which can be solved and which cannot be. Here you are thinking of a general equation and telling that it cannot be, something cannot be done. Okay. You are not discriminating that, see, certain polynomials you can write roots like this. So that proof you will tell that group is solvable or not solvable, and it will discriminate that. Okay. But advantage of this, maybe I will tell later, that you can also talk about continuous functions like exponential, trigonometric, and say that roots cannot be written as exponential functions of the coefficients, because what you are using, all you are using is this action, and then the loop is formed. Anyway, now I will go to biquadratic. The final punch will come when we come to quintic. Okay. So now I consider biquadratic, and what we do now? H functions. So what are H functions? What will be H functions? F, G, root G is also included. Okay. So suppose we have biquadratic, x4 is bx cube plus cx square plus dx plus e, and we have 4 roots, each is as H functions, H1 of bc, be. Okay. So I write Ri is function of Hi. Okay. bc, be. R1, R2, R3, R4, 4 roots. Suppose I have where H type function is, H type is what? Whatever f, root f, that is G, or you can just say G and root G, because G includes f and things like that. Okay. So now I have included one more radical, but that is not enough for biquadratic. That is what I want to show now. Okay. So any idea Any idea you want to give? Okay. Based on what we did, what can you think now? So now you want to, this already includes one radical, because this is root f, plus you have one more radical. So you should have some mechanism in terms of permutation which will take care of both the radicals. So you want to have something like two commutators, okay? Two commutators on 4 symbols, 1, 2, 3, 4, okay? So let me write that, not easy, difficult. So I write 1, 2, 3, 1, 2, 3 and 2, 3, 4. Commutator. See, these are permutations on 1, 2, 3, 4. Okay. And this comes out to be 1, 4 and 2, 3. You can check later on. All that we want is roots are shifted, but this side remains same. So here first root goes to fourth, second goes to third. Okay, so roots are shifted. Now we want to show that each side forms a loop. That is not changed. But what is special about this? Okay, see 1, 2, 3 itself is a commutator. Okay, so 1, 2, 3 is 1, 2, 2, 3. So is it clear? That is by action of this, okay, this 1, 2, 3, because this is a commutator, these G type functions will form a loop, because that is already seen in the earlier step. But now this 1, 2, 3 is again a commutator, so other root also will be taken care of by this commutator, which is a root G type of function. Okay, so that will also come to a loop. Is this clear? Because it will, see, after G forms a loop, this 1, 2, 2, 3, 1, 2 inverse, 2, 3 inverse will take care of this root G also, because root G will move and come back. Okay, G is already a loop because of this, but one more level of commutator will give you that root G. Is this clear? Huh? Okay. See, this in group theory language is that you are finding commutator subgroups of group. So commutator subgroup of S2 is trivial already. Okay, we don't need any commutator there. Commutator group of S3 is A3, which is not trivial. So you need one, and then A3 is order 3, which is abelian. So its commutator group is again trivial. So you want commutator chain of commutator groups to get to identity element in finite steps. Okay. So how many steps? Okay, 2 steps for S3, and for S4, the first commutator subgroup is A4. Then you get again a non-trivial commutator subgroup, and then third step you get it to trivial. Whereas now, finally, what happens to S5? Okay, in group theory language, easy to describe that commutator subgroup of S5 is A5, and commutator subgroup of A5 remains A5. And then how any number of commutator you keep doing, it remains A5. So it never comes to identity element. Okay. So the version of group theory that is used generally is A5 is simple. See, because commutator subgroup is normal. Okay. Once you have hit a subgroup which does not have any normal subgroup, then commutator subgroup will stay as it. So A5 is simple is used in some sense in this proof also. Because if I denote by commutator subgroup of S5, then that is A5. Then I take second level of commutator S5, which is commutator of A5, which is again A5. See, if you take all 120 symbols on 5 letters, okay, and take 120 into 120 commutators if you form, okay, and cancel out the repeated elements that you get, then you get 60 elements. Then again you form commutator 60 into 60, but you see that same 60 you get again. So A5 stays there. Then you keep doing commutator subgroup remains same. So this does not happen before 5. Why? because you don't have enough number of symbols there. That is, in S4, you go to identity element. S4 goes to A4, then smaller subgroup. And the number of steps is also, you can see here also the correspondence between the number of steps. Now, in terms of this Arnold's idea, this, that is, you need any number of commutators you further use. You cannot do this argument. That means any number of commutators is not enough. So, I want to write a theorem that the final theorem, that is Abel's theorem, is that roots of Quintic cannot be written in terms of radicals. Cannot be written in terms of coefficients by using radicals, by using algebraic operations and radicals. Any number of radicals we use. Okay. So, idea is simple here. So, this you try to take action of this now. So, now the idea is clear what to do. You take a permutation, its action. Then you try to write the commutators. Okay. So, what I do is 1, 2, 3 and okay. So, in general I will write ijk klm I get jkm. This is what happens in case of 5, because your 5 symbols are available. Okay. Now, by virtue of this formula, so you can put anything 1, 2, 3, 2, 3, 5, something like this. This cycle can be further written as commutator of another 2, 3 cycles. Okay. So, you can replace ijk here and write, so you will get something like this, but these are also again 3 cycles. So, any number of commutators you try, okay, you cannot get identity element in some sense. That is, this nested radicals, okay, will not give you the formula in terms of radicals. So, suppose if I have 5 radicals, if I want to write in terms of, say, suppose 5 nested radicals, okay, then I can write here more than 5 such commutator brackets and show that it is not possible. Okay, just like I proved for biquadratic or cubic. So, here you can do this any number of times, shows that any root h, root of root h, you go ahead. So, any finite number, say 100 radicals, then I can continue this process 100 times and come up with a contradiction that you cannot write, because this process can be indefinitely continued, okay, for 5. And the reason, you can either say like this or you can express in this form. These are equivalent versions of the same thing. So, this is one of the great results and kind of proof where okay, I have not told you a few things, so it could be made more elaborate, but in given time. Okay. So, I hope that I have communicated the idea that you take action of permutation on the roots and try to understand how root of a complex number behaves when there is a loop, okay, and you take square root, it does not remain loop. That is the main idea. So, fixed complex number, its root will change, okay, but this commutator thing will bring it back. So, that is main idea. And when you hit n equal to 5, you can take nested commutators indefinitely. So, this process continues, okay, indefinitely. You can have n equal to 10, and with patience you can write 10 commutator brackets and see that such function cannot exist. So, no radical, any number of radicals is not enough. That means roots cannot be written in terms of in radicals of the coefficients. Okay. So, that is in some sense elementary proof, but getting into more details is possible. For example, one should actually tell what is square root of z, why all this, one can make more elaborate, how root shifts, okay, how to make this root z function continuous, single value continuous function by taking it into the Riemann surface of square root of z, okay, you take two sheets where one value goes in the right half plane, other goes in the left half plane, then you attach those two and consider a single valued continuous root function and things like that. But those details I have not told you, but the general idea behind this Arnold's proof simplified many times, and Arnold never wrote, for example, the proof, he only taught in the classroom, and then later on that got transformed into book and articles, and as I told, till today, last year, people are writing articles on this. So because this is theorem of interest and old big theorem, so okay, that's all I wanted to tell. Questions you can ask.
What is not clear explanation, why the
Why complex?
commutators?
Commutators, because on one hand, see, one commutator will bring back the shift of roots, which is just taken place because of taking square root. So square root will shift. So z, so a loop at z, but square root of z will not be a loop, it will shift, because the argument will change from theta to theta plus 2 pi. So when square root is taken, it will go to theta by 2 plus pi. So many times, okay, in case of 2, if you do it even number of times, it will keep eating same. But if you take cube root or fourth root, okay, it will keep shifting from 1 2 pi by 2k pi by n, 2 pi by n times it will get shifted. So commutator will bring it to back to the original position. That is why commutators are used, so that if you assume that the roots are written in terms of those many radicals, then same amount of commutators will bring back on one side, but the roots are already shifted. So that is relation between these commutators and shifting of roots. Results. The direct Arnold student who heard this exposition by Arnold is Alex Ziv. He has written a book, I forgot the name of the book. Proof of Abel's theorem or something like that. Then this 2022 article is by Paul Raymond. This is Abel-Ruffini theorem, complex but not complicated. Complex means complex numbers are used. Abel-Ruffini theorem, complex but not complicated. This is monthly article, I think. Yes, American Mathematical Monthly, 2022. And if you want historical thing, then this book is nice, Irving. Beyond the quadratic equation. Beyond the quadratic. Mathematical Association, 2013. Here a lot of historical comments about quadratic, cubic, quartic, as well as what Abel did and what Galois did. There is one more book, I will tell you, I will communicate maybe, which is original Abel's proof is described. That is, the title itself is Abel's proof. Pezic, I think, author. Which is again different. I mean, this is neither Galois theory nor this type of idea, but here is his original proof, which is based on, see, Abel's ideas were based on French school, especially Descartes' then Vitae, Lagrange and Cauchy. The permutation idea is by Lagrange basically. So Abel capitalized on all this especially, and there was another person who is not French but Italian, Ruffini. He first thought about impossibility. Otherwise, like biquadratic, you can keep continuing like even Euler did. You keep trying that it could be written. The roots could be written as, but he was first person who hit this point that think of this, that you prove that it cannot be written. But his proofs had gaps and things like that. And those days, it depended on whether great mathematicians approve. So Lagrange never paid attention to his proofs and things like that. But his proof is 1799, Ruffini. And Abel's proof is 1824 first version and 1826 a longer version where elaborate proof is given. And Galois paper came in 1830. So Abel certainly didn't know any Galois theory. As such, ideas could be overlapping. And even Galois paper got published in 1846, much later.